Okay, lesson 3 is orbits and satellites. So what we know is that to launch a satellite, there's a minimum speed for it to get into Earth's orbit. So kind of the idea on how to get there, we talked about projectiles, where the vertical and horizontal components of a motion act independently. For the projectile problems we worked on, there was an unstated assumption that the Earth was flat. Okay, so that when we shot something, that the Earth wasn't curving away from it. However, we know that the Earth is in fact spherical, although not perfectly so. With this in mind, Sir Isaac Newton reasoned that some strange things would happen if one could horizontally project an object at high speeds. So at low speeds, a projectile will fall and hit the ground in a short time. As the speed of the horizontal projectile is increased, it will land further and further away from the starting point. All things that we know. For a flat Earth, a projectile will always hit the ground, no matter how fast it went. Gravity would pull it down. However, since the Earth is round, the curvature of the Earth affects where the projectile lands. So this diagram here is trying to show that if we were really high up here and shot something, it'll land moderately close. And then as much as we speed it up, it'll start to land further and further around the Earth. At some point, if we shoot it with a high enough velocity or launch it at a high enough velocity, it will actually orbit the Earth. Okay, so again, the greater the horizontal speed of the projectile, the more the Earth's curvature comes into play. Eventually, a critical speed is reached where even though the projectile is in constant free fall, it will not hit the Earth. Rather, it'll become a satellite in orbit around the Earth. So a satellite is something that's circling around a planet, a moon, etc. And so the Earth is a satellite of the sun, the moon is, and the space telescope are satellites of Earth. All right, so Newton was able to calculate the speed required to put an object into orbit, which will just skim the surface of a smooth Earth. Newton realized that a satellite orbiting the sun, the Earth, or some other body is simply a case of uniform circular motion. He reasoned that the gravitational force would act as the centripetal force for a circular orbit. Okay, so again, if something is orbiting another object, so if this was our Earth and we have something orbiting, he says that this is uniform circular motion where we have a centripetal force. Okay, and that centripetal force needs to just be gravity. All right, so centripetal force is equal to gravity in this case. We know that the centripetal force is equal to mass of whatever's being orbited. Whatever's doing the orbiting. Velocity of that object squared divided by the radius that it is apart. Force of gravity is equal to our force of attraction. So G, mass 1, mass 2 over r squared, where one of these masses will be the mass of the Earth and the other will be the mass orbiting. So what they're saying here is that the little m is the mass of orbiting object. So m's cancel. We can cancel one of our r's, and we're left with v squared equals g, big M, which is the mass of the body being orbited. So this is usually like our planet, whatever's in the center, divided by the radius that they are separated by. This equation is not on your formula sheet, but knowing that the gravitational force and the centripetal force need to be equal for a satellite, we should be able to get to this equation. All right, we are limiting ourselves to circular and not elliptical orbits. So we're going to assume perfect circular motion. And again, that's not necessarily the case, but we're going to have to go with it to make this work in our case without too much math. Okay, one thing to note, you're going to need the table from page 22 of your dynamics workbook for some of these questions because I didn't include the masses of these planets, so you may want to dig that out again. Okay, so what is the speed of orbit for a satellite orbiting Saturn if the radius of orbit is 6.43 times 10 to the 7? Okay, so we're looking for velocity. We have a radius of 6.43 times 10 to the 7 meters. So what we're going to do, we need the mass of Saturn. And if you look at that sheet, it's 5.67 times 10 to the 26 kilograms. So we know FC is equal to FG. You're going to have to show this on your worksheets and stuff. So make sure that you actually understand how to get here. So we have the mass, V squared over R, and that's equal to G, M. And I'm going to put mass 1, mass 2. So maybe planet, and this would be like our satellite. This is the mass of our satellite as well, divided by R squared. So masses of satellites masses of satellites cancel, so does R and the squared on this side. We're left with V squared is equal to G. I'm going to get rid of that squared, sorry. Mass of the planet over radius. So our velocity will be 6.67 times 10 to the negative 11 times 5.67 times 10 to the 26 kilograms all over the radius. Separating them is 6.43 times 10 to the 7 meters. And we need to square root that. Don't forget to square root. This equals 2.43 times 10 to the 4 meters per second. So that is the speed of a satellite if we have a radius around Saturn of 6.43 times 10 to the 7 meters. An artificial satellite in orbit around the Earth has a speed of 7.6 times 10 to the 3 meters per second. How far above Earth's surface is the satellite orbiting? So I'm just going to use our equation from the first question or first example there. Now that we know how to derive it, I feel like we can just go ahead with it. And we've done it once on our piece of paper. So V squared equals G, mass of the Earth in this case, mass of the planet divided by R. So we have the speed, we're looking for R. R is equal to G, mass of the Earth divided by V squared. So this is 6.67 times 10 to the negative 11. I just skipped the units for G because they're so massive. And I'm going to put everything else in, mostly because I run out of space all the time. And we need to divide by 7.6 times 10 to the 3 meters per second. Oopsie, squared. So I got a radius of 6.89 times 10 to the 6 meters. Now this is the distance from the center of the Earth to our satellite in orbit. And we're looking for how far above this Earth's surface. So we need to subtract the radius of Earth. So 6.37 times 10 to the 6 is the radius of Earth. And what we get is that we are 5.2 times 10 to the 5 meters above the surface of the Earth. I got 5.2, so a bit of a rounding difference with the original answer here, but no big deal. Okay, satellites, the period of orbit. So, if a question asks for the period, we use the centripetal force equation, which involves the period instead of the speed equation. So like before, the centripetal force is still provided by gravity, so Fc is equal to Fg. We're just using a different Fc formula. We can simplify that equation a little bit here, and we get 4 pi squared is equal to big G, the mass of the planet still, and R cubed. This is Kepler's third law of planetary motion, which we'll cover one more time at the end of this, but it was from our dynamics notes. And it said that the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. So all he was saying was that the period squared is equal to some sort of equation with the radius cubed. All right, a couple more examples here. So the average distance from the center of the Earth to the center of the moon is 3.85 times 10 to the 8 meters. That should just be a period. What is the period of orbit of the moon around the Earth? So again, we have the radius. We have the mass of the Earth. It's on our formula sheet, 5.97 times 10 to the 24 kilograms. And we are looking for T. Okay, so using our formula from our previous page here, T squared equals 4 pi squared over G, mass of the Earth, radius cubed. So T is equal to the square root of 4 pi squared and the radius cubed, so 3.85 cubed all over 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 kilograms. Make sure you are using the E button on your calculator for the scientific notation. When you divide otherwise and you don't use proper bracketing, you're going to get the wrong answer. Okay, so make sure you use proper brackets and or the E button on your calculator. For T, I get 2.379 times 10 to the 6. Now that's a giant number. The reason is this is in seconds. Now we typically don't talk about how long it takes in seconds. So if we want to convert that into days, just a little bit of unit conversion here. So 60 seconds in 1 minute, 60 minutes in 1 hour, and 1 day is 24 hours. In the end, I get 27.5 days. All right, at what height above the Earth must a satellite be positioned in order to have a period of orbit of 10 hours? So we are looking for the radius, because with the radius, I can find the Earth, or subtract the Earth's radius to find the height. We have the period of rotation is 10 hours. Now, period of rotation must be in seconds. So our first step is to convert this. So 10 hours is equal to 36,000 seconds. All right, we have our formula where T squared equals 4 pi squared G, mass of the Earth, radius cubed. If we're looking for radius, we get radius cubed is equal to T squared G, mass of the Earth, all over 4 pi squared. So radius is equal to the cubed root of 36,000 seconds times 6.67 times 10 to the negative 11 times the mass of the Earth is 5.97 times 10 to the 24 kilograms. All over, oh, sorry, period should be squared, 4 pi squared. We end up getting 2.356 times 10 to the 7 meters. Again, this is the radius between the center of the Earth and the center of the satellite. So if we subtract the radius of Earth, so minus 6.37 times 10 to the 6 meters, we get 1.7 times 10 to the 7 meters above Earth's surface. All right, just a little bit more about Kepler. We've kind of seen this already. Kepler stole somebody else's data, used it to prove that Mars's orbit is an ellipse. He discovered the 3 laws of planetary motion, which we've seen before. Planets orbit the sun in elliptical orbits with the sun at one focus of the ellipse. A straight line joining the sun to a planet sweeps out in equal areas in equal times. So again, if this was 1 day, and this is 1 day, this is 1 day, the areas here are the same. The cube of a planet's mean distance from the sun is proportional to the square of the period of revolution. We just calculated that using our formulas.